This is the first lesson I'm going to record. So this is the lesson for October 16th. Just some friendly reminders is to make sure that you're working on your research IA assignment because I will be looking at those and meeting with you after I come back and starting that meeting process with each and all of you. So please make sure that you have your research IA assignment done by the end of the day on Monday. And then also for tonight, what I would like you to do is to make sure that you are making VESPR flashcards, so that way you just know what the shapes are for every bond shape that could happen between covalent bonds. For your do now, what I would like you to do in your notebooks is to determine the coordinate bond and the structure that happens in the ammonium ion, and then tell me how it's made. So make sure that you're not just like doing the shape of it and making like one singular diagram for it. At least like make two or three to show how the one hydrogen is bonded theoretically to form and make the ammonium bond. So make sure that you're showing the lone pair, make sure that you're showing how the lone pair is donated to that of the hydrogen that's positive, and then also make sure that you, in your final diagram, show that three hydrogens are bonded to ammonia and the one hydrogen has that arrow bond on it. So go ahead, draw that in your notebooks in the steps to show how the coordinate bond is done. All right, now that you have done that, it is time to talk about the two types of bonds in covalent structures. So sigma bonds are formed when two orbitals essentially directly overlap one another. And so it can be either two S's, an S and a P orbital, P's and P's, and especially D orbitals that allow these sigma bonds to form. Now, what I want to tell you, every covalent bond does have a sigma bond in it. However, there is no plane and a zero electron density that goes through it. It is just the two species sharing that bond overlap with one another. So again, every bond has a sigma bond, whether it be a single, double, or triple bond. The other type of bond is known as a pi bond, and this is formed by not essentially an overlap between the orbitals, but essentially there are sideways on each other or parallel to where the electron density between them is above and below the areas of symmetry, which the area of symmetry is between the two species and they form essentially like line structures, as you can see right here. And the pi bond is formed between these two orbitals and the orbitals above and the orbitals below. So now that it does have symmetry between them, you can see that there's symmetry above and below as it forms essentially domain structures where the electrons can fall into. Now, with pi bonds, the line of symmetry that is there is where the sigma bond can be located. So make sure that you know that sigma bonds are all single, double, and triple bonds, but pi bonds only encompass both double bonds and triple bonds. So what I would like you to do is to look at these structures and determine which one is the pi bond and which ones have sigma bonds. So you will notice that all of these right away should have sigma bonds. The only one that has a pi bond is this guy right here, due to both orbitals being parallel to one another. So that is the difference between sigma and pi bonds, just so that you understand what a sigma bond is and what a pi bond is. Now it's time to get into what we know as VESPR theory. So VESPR theory is valence shell electron pair repulsion theory, which essentially states that in a small molecule, there are pairs of valence electrons that are arranged as far apart from each other as possible. Now, VESPR theory only applies to things that are covalently bonded. So far we have dealt with structural formulas and how to determine formulas, whether it be empirical or molecular formulas, but now we're actually going to see how these shapes are arranged. I will tell you, if you are testing for SL, the first five that I go over are generally what you need to know. If you're testing for higher level, all of these shapes are what you're going to have to memorize and understand how they are formed. So the first two easy ones, one is linear and the other one is bent. So linear is when two atoms are bonded to the central atom with no lone pairs of electrons on the central atom. So they have no lone pairs, it forms a straight line. However, we get into what we know as bent, where we have essentially two atoms bonded to the central atom, where one or more lone pairs of the electrons are on that central atom, therefore pushing it down. Now, I should have said this before going deeper into the slide. We have what we know as molecular geometry, which are these shapes, and then we also have what is known as electron domains, where essentially we include the lone pairs. Now, molecular geometry does not include lone pairs, electron domains do. So keep that in mind. Right now, we're just talking about molecular geometries. The next two shapes that we have are trigonal planar, which essentially makes a very flat triangle. There's no like pyramid shape with it. It's essentially when you had three atoms bonded to a central atom, no lone pairs, etc., with on the central atom. Now, a good example of this would be boron fluoride, where you had the boron in the center and fluorine surrounding it. Now, remember, boron only has three electrons that it can get away or donate or share with a species. So boron breaks that mold of what we know as the octet rule. So therefore, it does allow this to trigonal planar shape to take form. And then the next shape that we have is by trigonal pyramidal, where we have three atoms bonded to the central atom and one lone pair of electrons on the central atom. So an example of this would be ammonia, because on the nitrogen we have one lone pair, but we also have three hydrogens bonded to it, and that lone pair essentially pushes down on those hydrogens to make them slightly bent to give you the pyramidal shape. Now, the next one we have is known as tetrahedral, where four atoms are bonded to the central atom, no lone pairs of electrons that are on the central atom. Now, this is essentially like your methane example, where we have a carbon in the center and four hydrogens surrounding it. So make sure we know that this is an example of methane. And methane, and majority of carbon structures that have four bonds, will have that shape. Trigonal bipyramidal is essentially when five atoms are bonded to one central atom, and these are when we get into the octet rule exception. Now, phosphorus and sulfur usually break this octet rule um, exception, as you know, as I have taught you, that they are allowed to have more than just one species bonded to it because it breaks that octet rule from what we know. That's what trigonal bipyramidal is. It has five bonds attached to it, no lone pairs essentially. Now, seesaw is a little bit different. So it's a derivative of the trigonal bipyramidal. However, it replaces one of those bonds with a lone pair. So now we have what we can see is four bonded species, but one lone pair on the atom. So note that there are three trigonal bipyramidal shape derivatives. The shape comes from pulling off atoms from the flare triangle, not on the top or the bottom. So the flare triangle is what we have as this little species here, and I'll go back to show you. So the flare triangle is that trigonal planar shape that we have there, and usually it takes that shape and the derivatives from that shape that we know. T-shaped is also a derivative of trigonal bipyramidal, and it just removes another bond and it has two lone pairs on it. And then we get back to the derivative, which essentially is three lone pairs attached to the species that has the electron domain of trigonal bipyramidal. However, there are three lone pairs rather than two or one. So all of these are derivatives. So we go all the way back up to this slide, where linear doesn't have to just be two things bonded to a species. Linear can also be you have lone pairs on the species that's in the center of the atom, giving you a linear shape. The last three are exceptions as well, and they deal with the octahedral term of the electrodomain. So octahedral is essentially the electron domain of this three shapes, and then the rest basically are additional molecular geometries from octahedral that base off lone pairs that the central atom has. So octahedral is six atoms bonded to the central atom. Square pyramidal is essentially a derivative of the octahedral but has one lone pair on it, either top or bottom. And then square planar is essentially a derivative of the octahedral shape but has two lone pairs on it. So now that we have gone through all of that, let's go all the way back and let me just tell you the essential electron domains, okay? So the electron domains are as following. You have linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. All of those are essentially your electron domain geometries. The molecular geometry is paired off from those species that we know as electron domain. So you do need to know the five. If you're an SL, these are the five that you need to memorize that are essential to understanding the molecular geometry and shape of species. If you are taking higher level, you have to memorize all of these shapes. Now, First one, linear, two bonded species on the central atom. Forms a straight line. Trigonoplanar is also an electron pair geometry, or what we call an electron domain. So we have trigonoplanar, which again, three species attached or three bonds attached to the central atom, but this is where we also get our bent shape. Now, bent shape essentially means that we're taking one of these bonds away and allowing it to be a lone pair. Now, lone pairs are in the electron domain geometry. They are not in the molecular domain geometry, okay? Then you have tetrahedral, which tetrahedral has four bonds attached to the central atom. But if we take one away, we get trigonal pyramidal. And then if you take two away, you get bent. So if we look at water, water has an electron domain of tetrahedral, but has a shape of bent. If we look at ammonia, which is NH3, it has a electron domain of tetrahedral, but a molecular geometry of trigonal pyramidal. Then when you have five bonds attached to the central atom, you get trigonal bipyramidal, which is again this shape. One lone pair, you get seesaw or seahorse in this lovely diagram. Two lone pairs, you get T-shaped. Three lone pairs, you get linear. Okay? Basically, species that you need to know from the electron domain. Octahedral gets a little crazier. Octahedral, six bonded species around the central atom. One lone pair is square pyramidal, two lone pairs is square planar, three lone pairs is T-shaped, and then four lone pairs is linear. Now, this is the first slide you're going to be making your note cards and flashcards out of. The second slide that you need to make sure that you have as well are the bond angles. So bond angles are a certain point in aspect, and these are free give me points if you're ever asked this on the test. So linear obviously makes a straight line, it's 180. When you have trigonal planar, it is 120 if it doesn't have a lone pair. If it does have a lone pair and it's bent, it's 117.5. Now, tetrahedral is 109.5. There are exceptions to this. For example, if we add a lone pair for ammonia, it's 107. If you add two lone pairs, it's going to push down on those atoms more, and then you have a bond angle of 104.5. All of these are what you need to memorize. Trigonal bipyramidal, in the plane, it's 120. The bond angle between this x and the second x here, that would be 90 degrees. Now, again, these get crazy as we continue on. Lone pairs change, like the 120-ish area, which is in the plane, to 117. But as you notice, it all stays 90 throughout, even through T-shape. And then when we get to linear, it's 180 again. Now, for this lovely shape, the octahedral shape, 180 from this x to this x, but everything else is 90. When we add lone pairs, it decreases by 3 to 87, and then when we get to square planar, again, it's 90 again. So you need to make flashcards not only of the electron domains, but the shapes, and then also know the bond angles for everything. So realistically, all the shapes, there are 12. You need to memorize all of them. You need to memorize how many bonded species there are, how many lone pairs, what the actual electron domain is, and then also the bond angles. So here is the best thing that you need to do when you're making these flashcards. Draw an example structure. These example structures can be here, and they can also be found here. And then on the back of it, you're going to put what the name of it is, and then also what the bond angle is. Maybe look online as well to see if there's any examples that have these types of shapes. So now we are going to work through making one of these and determining the bond angle for it. So what is the bond angle between H, C, and H in methane? Well, we know that if we were to draw the Lewis dot structure of methane, it would look a lot like this. So that's where you're going to start. You're going to start by drawing the Lewis dot structure for it, and then you're going to count the amount of areas of electron domains that are around the central atom. So we have 1, 2, 3, 4 bonds. So we have 4 bonds around it. So when we think about this, we have a central domain of carbon, which is the center atom, and we have 4 domains around it. If we have 4 domains around the central atom, the shape would obviously be essentially tetrahedral. So you use the 4 domains to use and choose the shape. Now, electron domains also includes the lone pairs. So when we're talking about electron domains, we also need to include the lone pairs. So therefore, we know there's 4 domains around it. So therefore, the shape is tetrahedral. If we go deeper, we know that tetrahedral, we need to make sure that we're going to actually draw it precisely and make sure that we are also looking at the appropriate bond angles and size. And if we go back in this lovely video, we will see that you have a bond angle of 109.5. So here's what I would like you to do for the next 5 to 7 minutes. What I want you to do is to determine the bond angle that is in ammonia between H, N, and H, and then also determine the bond angle in water, which is H, O, and H. Now these two are a little hard. Before I let you go, I will tell you, you probably want to use this slide in the video and this slide in the video. If you're looking at the slideshow, it is slide 113 and 114. So take the minute or 5, pause the video, and then come back when you are complete. All right, now that you have done that, it's time to go over some tips and tricks that you need to know in order to determine these things. We use the term electron domain rather than pairs of electrons to avoid confusion. In CO2, there are 4 pairs of electron, but only 2 areas of where the electron densities are, because this is due to the double bond and the pi bonds that are there. So we say this as the electron domain has 2, and therefore the shape between the carbons and the oxygens gives you a linear shape. Sometimes the central atom can bond happily without having a full pair of electrons, so don't get caught on the confusions of things. And then you also have to know repulsion between pairs of electrons. Bonding pair and bonding pair, there is no repulsion. It's going to have the angle that you have and know. Now, if we add lone pairs to the bonding pairs, then it's going to increase repulsion and therefore decrease the bond. And then if you have lone pair against lone pair, it's going to again increase the repulsion and push on the species that are bonded. So sometimes you have to predict and share ions. So try to predict the shape of the ammonium ion and then the chlorine ion as well. Okay, so ClF4. Those two are a little harder. And what I would like you to do is to start with like a lovely notebook paper, pull it out, put an exit ticket, and try to predict the shape of these. This is not what I'm going to be grading. However, on slide 126 is what I need you to turn into the bin before you leave. Okay, here is an exam-like question for you. Chlorine can form molecules and ions that contain only chlorine or that contain chlorine combined with other elements. Use your understanding of the electron pair repulsion theory to draw the shape of the arsenic chloride molecule and the shape of the chlorine 3 plus ion. Make sure to include any lone pairs of the electrons that can be influenced in this shape. You may have to look up the chlorine 3 plus ion so that way you can know what the Lewis dot structure is, okay? And then name the shape made by the atom in the arsenic chloride molecule and the chlorine 3 plus ion, okay? This is what you're going to be turning in before you leave class. If you don't finish it by the end of class, just please turn it in and put it in the bin tomorrow. Tomorrow will be a work day for you guys to work on your VESPR packets. So tonight, make sure that you have those flashcards ready to go and then bring them in so you guys can work on your VESPR packets. I hope you guys have a great rest of your day and a great weekend, because if you have not watched this video, then it's important that you guys have a great weekend and also get your work done before I come back. And then I will have another video for you guys on Monday. Have a great day.